just to repeat a little bit about the material model, what is that? That's, you can say, a mathematical description of how the material behaves. And usually you have a lot of different phenomena, but in this project and with high pressure die casted material, we will focus especially on the effect of the grain size. As you saw in the picture before, you have quite different grain size on the outer surface of the component and in the center, and this needs to be taken into account. Even if we create a very good physical base model, we will always require material testing. So in some cases it can be a little bit more advanced testing with higher strain rates, but that needs to be included even if we know the microstructure. So if we look at the mechanical properties of high pressure die casted material, this is a typical stress strain curve. If you test a number of specimens, you will see that you have quite small variation in the yield stress and ultimate tensile stress, but you have quite large variation in failure strain. As you can see here in this example, you have a variation between 11 and 16.5%, and you need to take care of this. Of course, you can be very conservative, design your system for 11%, but with more samples testing, you will have your lowest value will go down more than that. And that's the reason why we have introduced something called probability. Deterministic modeling, then you have one value where you get failure, but including probability means that you can calculate the probability of failure. So as an example here on the on the right hand side, we have one element. I don't know if the animation is running. No, it's not. But if you deform this element, so on the x-axis you have the equivalent plastic strain versus the probability. So in this case it's a material with 12.5% of elongation or strain for the mean failure. So you can see when you reach 50%, then you reach this failure strain. 50% probability, that means that 50% of your specimen will fail when you come to this deformation. Another thing with failure strain is that it is dependent on your stress state. So we usually define it with something called the stress triaxiality, and that is the stress condition. So typically in a uniaxial tensile test like this, where you have a hole in the center, then you have a value of 0.33, and then if you have more shear-like behavior, then you close up to almost 0. And in plane strain condition, you have approximately 0.58. So you need to create these failure curves. This represents the failure strain at that current stress triaxiality. And you need to take into account the microstructure. So in our case, it will be different on the outer layer of the component and in the internal part of the component. And another challenge is the variation in failure strain that we need to take into account. Let's say that we test at a certain stress triaxiality, we get variations, but we don't have the same variation at another stress state. This needs to be taken into account, and that's one of the research questions we try to solve now in the Flexcrash project. So the dotted line represents 3 standard deviations from the mean value. So our hypothesis is that when you calculate your failure strain, because this is dependent, in a crash analysis, you don't have a constant stress triaxiality, it will vary. So you need to take care of that. But we do that, you can say, linearly. So as an example here, if we start with uniaxial tensile at time t1, we deform it, and we are 40% from the -3 sigma line. Then, when we go to the next time step with another stress triaxiality, in this case close to plane strain, then we start at the same, you can say, distance from the -3 sigma line. The other condition is that when we deform more in the first step, so we pass this -3 sigma line, then we are in the world of probability. So we need to take care of that in another way. So what we do then is that we follow the isoline. When we then change the stress triaxiality, so it's this, we move, so we have the same, we start with the same probability in the next step before we take that additional strain step. So that's the hypothesis, and that's something we need to prove in this project. Just to show you an example, this is a bending case. So when you post-process this is an example where we have implemented in Dyna. But now I think I will try to use, see if we can start is it possible with a mouse to try to, as you can see, when it changes color with probability, so 1 represents that all components have failed. So in this way, you can basically, when you design a system, you can choose at what probability will I design it for. Will I take the risk to have 10% or 20% or 50% when I design my system? So what we also have done to be able to resolve this very thin layer of small grain size in the component, if you use a solid model, for example, it becomes a very small element. The green area here, you can see that it's elements that are 0.1 millimeter. The time step will be extremely small in an explicit crash analysis. So what we propose is that we use something called thick shell, where you can define your material properties in different layers. So then you can easily include the skin effect. So in this example, I will try to start that. On the right-hand side, you have the thick shell model. It gives similar deformation behavior, but in this case, 17 times larger time step than the solid model, which saves a lot of time. Of course, when you do this discretization, you need to be accurate. So this example shows the force versus displacement, and as you can see, with one element, one T-shell through the thickness, we cannot really resolve the force displacement result, but with only 2 elements in the thickness direction, we can get approximately the same behavior as with the solid model. So if we talked about AM in the introduction, you can also introduce AM structures in this by, we also propose here to use this thick elements for that. It can be modeled. So if you look at some of the conclusions, the probability model has been implemented. You need to include the stress state dependency. The standard deviation at different stress states can be taken into account. Thick shells are very efficient for this kind of structures. And where we think 2 elements is enough through the thickness. And the next step and future work will be calibration of this model. That's the next step. So I think I will stop there.